All right. Let's get the slideshow started from here, but we're not going to start with the slideshow. I do want to make a couple of announcements first. Can't remember if I told you this before or not. No, I don't guess so. This is the first time we've met since I found this out. In fact, maybe since I did what I was about to say. Did I tell you that I got everything uploaded on Blackboard? I didn't tell you that. Okay. Last Thursday, it was probably after class. I think I was here till pretty close to 9 o'clock at night trying to get all the syllabi straightened up. Probably not quite that late. 7, okay. All the syllabi straightened up, and I gotten the research paper instructions corrected. My locator card I thought corrected. All the PowerPoints loaded for all my classes, and all the videos and other things done. Thought I had it all taken care of. Finally got it all put on files late Thursday. And then I found out they may approve me to teach an overload. Well, if I teach an overload, then I'm supposed to be here more hours to count for the overload. So then I have to go back and change my office hours. Now, I still don't know for sure, but it's a pretty good guess that I'll stay here till around 5:15 most Tuesdays and Thursdays. Before, I was having to leave at 3:30 because I thought they weren't paying me an overload. Well, I wasn't having to leave. I had to put it on my locator card. I was leaving at 3:30. But I was usually staying later to get things ready for the next day or the next week. So now I've gone through since then and updated all the syllabi to my new office hours and my locator card. I had to take all those out of my blackboards and put all the new ones back in. They're done. Okay, I hope they're all done. So you'll find on Blackboard now the syllabus, the corrected, updated syllabus, the research paper instructions, my locator card corrected, the 10 beautiful pictures from the Hubble Space Telescope, it's well worth a look, that file called Space Objects in Perspective, really an interesting comparison. I think you said you had one similar to it. Okay, let's see, what else? All the PowerPoints for all the chapters we'll be covering. I don't know if I found any others, and then I put the link so you can get to the YouTube videos. So it's all out there, ready to go. I can't think of anything else I really have to do. That's all done. Okay. There's that. And I can't remember if I said this to you recently. I think I said it early on, but maybe you didn't pick up on it. You can bring with you to every test a formula and equation sheet. Anything you want to write down from that chapter or from anything to have with you on the test. Because I'm not a big memorizer. I don't like to memorize. But in reality, if you were working for me, I'd say, go solve this problem. And I wouldn't want you to say, oh, I think I remember how you do this. Let me see if I can do it. No, I want you to look it up, and make sure you have the correct formula, the correct information, So basically, on every test, including the final, you can bring with you a formula and equation sheet. Anything you want to write on there that would help you think might help you on the test. Now, that said, remember, we finished chapter 14 last time. We started the lab for chapter 14 last time. We're going to finish that now. Then we'll pick up in 15. And then the last 30 minutes today, that's from 3 to 3:30, is when the test for chapter 14 is. So I felt really bad. I couldn't remember for sure if I told you you could have a formula and equation sheet. So if you haven't gotten that put together yet, if you want to be doing it sometime, you certainly can. Okay? Any questions? All right. So I think I'm going to minimize this so I can open this, because I think I was using this before too. Okay, where is it? I know it's hiding in there somewhere. This is a pain in the neck. I've opened it, and yet it's not visible. What a pain. I'm going to try opening it again. Still not visible. I'll try opening it again, because we do need it for the lab today. And why it's not opening beats me. Keeps jiggling as if it's trying to do something, but so far it's not doing anything that I can tell. Still not there. We'll try it again. Okay, now it's changed colors. I don't know. Why will this not open? Now, what I might have to do, I don't know why, is shut down everything else. Okay. I'll shut that. Now let me try this again. There it is. My word, that took forever. All right. Any questions? Anything we've done so far? Anything from the text in chapter 14? Okay. So, where were we on the lab? Celestial coordinates. We had done, hopefully you have read page 359. We had done part A, number 1, on 350. 2 and 3 on 361. 4, 5, and 6 on 363. And I think we finished 8 and 9 on page 364. Didn't we finish all those? Say that one more time. We stopped what? Halfway through 9. Okay. So we were still working with the star finder. So we got 11 hour, 19 hour, and 3 hour right ascension. Okay, so we still got, we're going to pick up on the last 3. Is that right? Who wants to go? All right, good deal. Okay. So we're looking for constellations now, not individual stars, like we did early on 9. How do you do, where do you start to do before you go to 1 hour right ascension? What's that? March 21st. Are you there already? Okay. And if you hold the string there, you'll see what happens there. Celestial equator and the ecliptic, the dash line and the circle there, they cross. Okay? And where do you go from there? 1 hour. Okay, wait. Be there. Okay. Count off 1 hour. You're right there. Okay. Now, it's right behind there, so you can't see. That looks like late March, early April. Maybe early April. So turn just a little bit until the first 2 days in April. Okay, somewhere right in there, I think would be good. and then you go plus 60. Where is plus? Yeah, above the celestial equator, about 2/3 the way up, and what constellation do you find there? Cassiopeia. Okay, I don't know how to pronounce it. I've heard it called Cassiopeia and Cassiopeia. I think Cassiopeia, like you said, was probably correct. Let me spell it for you. I'm going to try to get in front of my computer so it'll pick up. So this one will be Cassiopeia. 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 Now, when we get to, if we do get to go to the Stanford Planetarium, he usually tells the story of Cassiopeia and how it got there. I never saw it. To me, it looks like a big W in the sky, and I can sometimes pick it out. But what it's supposed to be is a woman sitting in a chair. And that's Cassiopeia, and she has been trapped there by Zeus or somebody, and Hera or somebody. Who wants to go to be next? Okay. So that was 1 hour plus 60. Okay, where do you begin?
March 21st.
Second?
March 21st.
So where do you put it? Yeah, okay, line it up there. Okay. Celestial equator and the ecliptic of the sun cross in the fall and in the spring equinox. Okay? And where do you go from there? 13 hours right ascension. All right, we can see exactly what date. What is that? Looks like it is 6, yeah, something right around October 6th. Send that around till it's there, October 6th. Oh, fantastic. Yeah. Oops, I'm going to try it again. Okay. You're zooming in on it. Okay.
And minus 50.
Minus 50. Yes, it's right there at the horizon. And what do you see there? Centaurus. C-N-T-A-U-R-U-S. Does anyone remember or know what or who Centaurus was? If I'm not mistaken, Horus means the bull. Centaurus was the mythological creature that had a man's body and head, but, well, a man's torso and head, but 4 legs, and the rest of them looked like a bull or a horse or something. Okay, I think that was Centaurus. Okay, constellation Centaurus. Who's next? Oh, you volunteered. All right. Where do you start? March 21st. Getting there. What happens on March 21st? What is it, ladies? Celestial equator and the sun's ecliptic. The dashed line is the ecliptic, dashed circle here is the ecliptic, and the solid circle here is the eclipse. It's right there. Really good. Yeah. Yeah, you see it crosses right on that. Okay. Now where do you count from there? 7 hours, right ascension. So where is that? Right into space. So we don't have to guess. That looks right around maybe the 1st of July. Yeah, something around the 1st of July. So scoot back down till that's under here. C-A-N-I-S, Canis Major, M-A-J-O-R. Anyone know what that means? What are these called right here? The point of them. Anyone know? Huh? Canine teeth, exactly. Canis, canine, and what is a canine? As opposed to a feline. A dog, yeah, the canine, these are your dog teeth. So this is the big dog. Major is big, the big dog. Somewhere on there is a little dog. So there's Canis major and Canis minor. You've got Canis major. Okay, that finishes what we're going to do under Part C, Celestial Globe, though we use the Star Finder. Now we move to Part D. All right. Now, I think I'll give it to Ricky. Not that you have to do anything now, but describe to the rest of the class. Yeah, we can get together if you want to, or you can stay where you are. It says, on the ecliptic, locate the position of the sun on June 21st. Where do you think the position of the sun is on June 21st? Roll that around until it finds June 21st. And by the way, this is almost redundant. It says, on the ecliptic, locate the position of the sun. Guess what? That's where the sun is anytime. It's always on the ecliptic. On June 21st, where do you see the sun be? Okay. The ecliptic is where the sun is. Right there it is. Somewhere right there. See this dashed line? A circle? That's the ecliptic. That's where the sun is. Now, note the sun's declination for that day. What is declination? What is declination of the sun? What does declination mean? You want to know how it goes down? Okay, wait just a second. Say that one more time.
How it goes down, where it sets.
Okay, now declination, if you turn back a couple of pages, on page 363, two coordinates called declination, right ascension in the first paragraph under Part B. The declination of a star, including the sun, is its angular distance measured in degrees between what? The celestial equator. Well, where's the celestial equator on this thing? It's the solid circle. So where is the sun in degrees above? It's in the north. I'll give you that. It's toward the North Pole. But where? How far, approximately? Can you approximate that angle? It's an angle we've seen before. And we'll see it again. 23.5 degrees. You're absolutely right. That's the maximum the sun is ever above the celestial equator. And on June 21st is when it reaches there. So that's where it is. Note the sun's declination for this day. Record it in the table 14.7, 14.1, 47.1, I can't read. Now, I'll apologize ahead of time. This is from the lab manual. I don't know who did this, but they were really sloppy. Notice on there, the first thing, June 21st date, and then it says the SEC of the sun. Southeastern Conference, second? No, that's supposed to be DEC. So on the table, that's a DEC. 47.2, that's a DEC. 47.3, that's a DEC. At least they were consistent in their error here. So it's DEC of the sun. So note that on that table. What's the declination of the sun on June 21st? Okay. Now you need to say it one of two ways. Either north or plus. I don't care which one you use. North or plus. 23.5 2.5 degrees north or plus 23.5 degrees, either one. Okay, you want to pass that to somebody else, maybe to Brian there, and he's going to find it on December 21st. Okay. Oh, wait. Sorry. Before you do that, let me go back. Okay. What we're supposed to do, and I'm going to show you all of it, and I'll give it back to Rick. Okay. June 21st. Okay, somewhere around here. Okay, June 21st. Right about there. I think that's where you had it. You tell me if I'm about where you had it. Is that about right? Okay. Now. Okay. When the sun is there, when we see the sun, guess what? You don't see any stars, right? Because it's daytime. And the sun bleaches out all the stars. You can't see them all. But if the sun were turned off all of a sudden, you see all those stars that you would normally see. And the star that's right behind the sun, then, you see those three in a row right there on the ecliptic? Okay? Which one is it? I can't remember. Let's line up this hole. June 21st. It's right past the 30th there. Right, that one right there. The sun is right over that on June 21st. Okay? So if we want, when the sun is rising, we turn this around until it gets right above the horizon. Right there. Sun's right over that star. So let's see what time that is. Right there. That looks to be about 4:40. So that's 4 o'clock, 20:40. About 4:40. Okay? a.m. Now this is based on north 40 degrees, I believe it is. I don't know, I found it somewhere here. Yeah, right here. North 40 degrees. So that's a little bit further north than we are. Most of the time in the summertime, the sun isn't quite that early for us. Further north you go, it gets earlier and earlier. Okay. Now I'll give it to Brian. You're to do the same thing. Oh, wait, no. Goodness, my brain isn't working. Because we need to also find when the sun sets. So it sets over the western horizon. So there's that star, right? That one. Okay, I'll let you turn it around so it's up before it goes set. All right. You might want to do the string or whatever to see about what time that is. About 7:20, 6 p.m., 7 p.m. About 7:20. Great. Okay. About 7:20 p.m. Okay. Now. Okay, we have then the sun rising. Was it 4:40? Whoa, let me get my dark ink. Okay. 4:40 a.m. Okay, that's when it rose. And when did it set? 7:20. Now, I like to use military time for that. What would that be? 19:20. So at 19:20, it set. And I won't use AM, PM because that indicates this. So this is sunrise. And this is sunset. Okay? So if I subtract those times, that's how long the sun was up. And that's the next thing it asks for. How many hours of daylight was that? Okay? Now when I go to subtract this, 0 from 0, 0. I can do that one. Okay? Now, I can't subtract 4 from 2, so what do? borrow 1 hour, this means, from here, leaving 18 hours, right? And how many minutes is an hour? 60. So I add 60 to 2, 6 to 2, 6 to 2, and that gives me 8. 20 minutes plus 60 minutes is 80 minutes. Now I can subtract, and what does that give me? 4, and then 4 from 8 is 4, 1. So 14 hours and 40 minutes of daylight, June 21st, when you're at 40 degrees north. Let's see if I can find where 40 degrees north is. There's 45 degrees north is Maine. So 40 degrees north would be about maybe New York City. New York City? Okay. So, that was the commercial. Okay. Somewhere around there. So it's a lot more date, probably a little bit. It's further north than we are. Now, how many hours of darkness you have then? We'll subtract that from 24. Okay? Except I don't want to subtract it from 24. I want to subtract it from 2360. Isn't that 24? 60 minutes being 1 more hour, that would be 24 hours. So subtract 1440 from 2360, which is 24, and what do you get? 0, 20, 2, yeah, you're right, 9. 9 hours and 20 minutes of darkness that day. Okay? Does everybody see how we got that? Okay. Finally now, Brian's turn. He's going to do the same? Yes.
Out of everything we just did, does it answer the
Yes.
question?
I meant to do that. Let's go back. It said, record that on table 47.1. We did. Now, let's go back to your question. That's excellent. Does the sun rise? Okay, I've got to find it again. Those 3 little stars out here they are. Right there, right? Okay. Does the sun rise due east? Is that what the question asks?
Does the sun rise exactly?
Yeah. And you see, here's where it's rising, right there, right? Okay. Here is due east. Is it rising due east? No, just a little bit north of east. Okay? So that's, I'm glad you caught that. So the answer is no, a little bit north of east. So number 10, does the sun rise exactly in the east on this day? No, it rises a little bit north of east. I think I told you about opening the blinds in my house in the summertime. When I open that back bathroom window blind, in the summertime, I get sun in. Facing due north, I still get sun coming in. Wintertime, not a bit. Spring, fall, not a bit. Only in the summer, it rises a little bit north of east. Very good. Now, and then we did rotate the globe till it sets, note the horizon, blah, blah, blah. So there we answered that. Okay. And we subtracted from 24 hours, which we used 2360. Okay, now repeat this for December 21st. So you do December 21st. So how are you going to begin? Okay. Where is the sun that day? Where's the sun always? On the, say again? On the ecliptic. The sun, that's where the sun is. It's on the ecliptic. That's where it eclipses. ellipse is everything behind it. So you see the ecliptic is down there. Now there's no star there, but you see it's that dash right there above that bright star there, that end of the dash. Turn that around till it's right. End of that dash. This way. So it's right. Okay. Keeping up with the dashes down right there. Okay. Okay, keep going. Okay, be careful now. Get near it. Keep going. Oh, you were fast. Right there, that end. Okay. Stretch the string around here till it's right on that horizon. See, it's that. Whoa, good turn. Right there. Yeah. Bring the string around till it's right over the end of that dash right there. You see that dash? Okay. Bring it on around. The string. Okay, yeah. No, the string around here. So the sunrise. That's sunrise. Okay. Now about what time is that? The clock right here. Okay, it's 7:40 maybe? So just past 7:30. It's halfway between there to 7:30. Okay. You can say that if you want to 7:45 or 7:40, it doesn't matter, whatever you want to say. 7:30, okay, say 7:30. Okay? Now, and by the way, where does the sun rise in? South of east. Due east, it won't be there, it'll be somewhere south of it. Okay, now let's take that dash, that end of that dash, spin it around till it sets. Did y'all record that? 7:30? I think is that what you said? Okay. Spin that dash around. No, the dash. This wheel. Okay. Yeah. Okay, so that one right there wasn't. Yeah. That end of that dash. Okay. Spin that around for just before it sets. Just as it sets. That's for the sun. Something like that. Yeah. Whoa, so. Okay. Yes. Yeah, it's setting right there. Bring the string around and see what time that is. Right there. That. First end of the dash. Tight, take it tight. Right about there. See, right when it goes into the right. Okay. You see the dash right there? Move it up to that. Yeah. Okay. Right. That dash. See the right hand end of that little dash there. Right there that goes up. Okay. What time you say? Okay. 4:20. You want to call it? I like rounded numbers. Okay. 4:20. So that would be the time of sunset. Okay? Now, they didn't ask you to write those, but did y'all record what those were? Sunrise was, what time did you say? 7:30? 7:30 a.m. And you said 4:20 p.m.? And what time would that be military? 16:20. Okay, again, we're going to have to borrow. So we'll borrow 1 hour from the 16, leaving it 15, right? Add what to 2? 60 minutes is 1 hour, so 60 plus 2 is 8. So that's about 50, and that would be 8 hours and 50 minutes of daylight. Are we filling in every... Oh! Did you tell me what the declination of the sun was that day? I forgot to ask you that. Yeah. Remember, well, you can turn that back around till that's at the bottom. Anyone want to hazard a guess? Minus 23.5 degrees, or 23:30, or 23:30 south, or however you want to say it. It's south of the equator, meaning minus. And since, on the earlier things, the declinations were given as plus or minus, so I would say on that, for the one for June 21st, that would be plus 23:30, and Minus 2330 would be December 21st. Minus 23 degrees, 30 minutes. Okay? That's the declination, not seclination, or whatever that is. Okay, and then we just figured how many daylight hours was that? Okay. Have I done something wrong here? No, maybe not. Yeah, about 8 hours and 50 minutes. Then subtract that from 24, which I'll use 2360 again. 850. And what will that be? Say again? 1510. Okay, a very good year. Okay. Now, these may not be exact, but up there, very little daylight and lots of darkness on December 21st. Okay? Now, March 21st, right behind you there. Right behind you. He slid it. Okay, what will you do first? What we were doing before. You set March 21st in there. Yeah. Ricky did that one. Brian did that. We do it March 21st. So set that day first. Okay, March 21st. What do you know about March 21st? Because this is the celestial equator. Where does that mean the sun is that day? Declination of the sun. The sun is always on the ecliptic? No. Okay. You said it crosses the celestial equator. It's 0! It's sitting right there smack on top of it. Okay? So the declination of the sun, yeah, there, okay. 0 degrees. Okay? Now, you take that, that's where the sun is, we'll swing that around until it just is rising. That place right there where they cross. It's real easy to see.
What is rise?
Okay, see, this is the sun on that day. The sun on March 21st is sitting right over that all day long.
Yeah.
So you rotate that around until it comes over the horizon. No, rotate the circle.
Oh, that's the rise.
That's the horizon. This is the horizon of that day. So rotate the circle until that is just coming up over the horizon in the east. That place right there, that cross right there. Okay. All right. See what time that is. Put the string right across there. Yeah. 6 a.m. on the nose. Okay. Rotate it around till the sun's setting. You don't need writing. Okay. 6 a.m. So that same place. Rotate it around here till the sun is setting. Okay. Because that's the sun. The sun is on the ecliptic. On that day, that's where it is. Let's see what time that is. 6 p.m. So, how many hours of daylight do you have that day? 12. How many hours of darkness? 12. That's what we call it. What do we call it? Equal night and day. Okay? All right. Now, we're going to go up where it's cold to Altegard, Norway. Okay? Altegard, Norway. I'm going to clear this out of the way. Everybody got what you needed right here? Okay? All right. Now, they tell you Altegard, Norway, the latitude is 70 degrees north. That's up there, folks. So here's your globe, and here you are standing in Altegard, Norway. Okay? And you got a big, heavy coat on, okay, because it's cold up there. Okay? Now, 70 degrees north. You're standing here. Okay? That's where you are. Your zenith is up here, by the way. Oh, that's a very crooked line. There's your zenith. Here's your horizon in Altegard, Norway. Okay, with this being north. North. This being south. Okay? Now, you first put where you're on the globe. 70 degrees is awfully close to 90, isn't it? So that's 70 degrees north. This is the equator here, right? 70 degrees north is where you are in Altegard, Norway. So on the celestial sphere, I don't draw very good. Ooh, that's ugly, isn't it? Quit laughing at me. Okay. There is something like the celestial sphere. Where would be the celestial equator? Wouldn't that be 70 degrees from your zenith? So that's something like that. I may not even have it enough. In fact, I think I need to make it a little bit more. Okay? Because you only have 20 degrees here. That's about right. So this is 70 degrees. This is celestial equator, and your zenith is 70 degrees north of that. Does that make sense? Okay? Meaning how much the celestial equator is how far above the southern horizon? 20 degrees. So this is 20 degrees here. Okay? Now, what is on June 21st, what is the declination of the sun on that day? Ricky knows the answer to that. Sun's the same place it was when you're in Norway as when you're in New York City or Philadelphia or anywhere. Where was the declination of the sun on June 21st? Huh? 23.5 north plus 23.30. The sun is there. Now, what is that declination measured from? The celestial equator. So that means if this is 20, the sun is a little bit more than that. Here's the sun on noon when you're in Altegard, Norway. It's right there. The declination of the sun, rather than seclination, that's 23 plus 23 degrees, 30 minutes. Now, how many hours of daylight? Okay? I'll have to cheat a little on this. We're going to have to find Altegard, Norway on the globe. Okay? Here's Norway. This is part of Scandinavia. Norway, Sweden, Finland. Denmark's down here. This is Norway. They don't really show Altegard here, but they do know it shows 60 degrees north, and this is called the Arctic Circle, which is 66.5 degrees north. So Altegard, Norway is somewhere north of that. That's 75 degrees north here, so it's somewhere just 5 degrees off. That's just about as north as you can get in Norway. You're up here, but the key is you're above the Arctic Circle. Got it? You're north of the Arctic Circle. Okay, you want to be the sun for me that day?
I still got questions about that.
Oh, okay.
It asked, what's the declination of the sun? What was your answer?
This answer is 23 degrees, 30 minutes north. It's on June 21st, the sun is always in the same place. And it's 23.5 degrees north of the celestial equator. That's as high as it'll ever go.
Even if you're that far north?
Everywhere on the globe, the sun is 23.5 degrees north of the celestial equator on June 21st. Everywhere. That's where it is. Terminally thinking is always there. Okay. Now, here's the sun. Can you see this spot right here, the very northern part of Norway? Okay? And can you still see it? Still see it? Okay, well, I'm not down on your level. Everywhere north of the Arctic Circle, that is in sight of the sun. The sun, the earth turns and is always not very bright, very low in the horizon, but everywhere north of the Arctic Circle. On June 21st, it never sets. Alaska and those other places, the land of the midnight sun, because it never sets on June 21st. Okay? Ever. Okay? Can you see that point right there? From where you see? Sit up where you can't. Well, if the table were a little lower, it's right there. And it's really low in the sky, but it's there. Everywhere above the Arctic Circle, the sun is shining in that the whole time. So the answer there, 24 hours of daylight. Not very bright daylight, because at noon, it's only 43 and a half degrees in the sky. That's less than halfway up. 90, 43 and a half is less. So at noon, it's not. But it never, what it does, now the east is just above the horizon. At noon, it gets up to 43 and a half. Then it sets, at noon, when it doesn't rise, it's already up. So a little above the horizon there, goes up to 23 and a half, goes back down, and then gets right above the horizon, and then comes back up again. And for a day or two or three, it's like that. It's 100 degrees more. Right at 66 and a half degrees, that's the only day you'll see it. And then at midnight, the sun's right on the horizon, but it's still showing. Okay, but the further north you go, it's a little off the horizon, and the further north you go, it'll be a little bit more off. And it'll be several days it never sets. Altogether, Norway never sets. How many hours of darkness?
That was the thing that confused me.
What's that?
I said, that was the thing that confused me. It was 43 and a half degrees
From the southern horizon.
Okay.
Yeah.
And then
When at noon. Yeah.
23 degrees, 23 and a half from the
Above the celestial equator.
celestial.
Okay. Now we go to December 21st. What's the declination of the sun on December 21st? Minus 23 degrees, 30 minutes. Everywhere on the globe, the sun is 23 and a half degrees below the celestial equator. So let's draw that in here. So let's take out the sun here. Woo! We're going to take out the sun. Shame on us. Oh, not that one, this one. Okay. And this and that. Okay. Woo, I erased part of my celestial sphere. Shame on me. Let me draw it back in there again. Okay. And where is it? You said minus 23 and a half. That's 23 and a half degrees south of the celestial equator. Where's the celestial equator? 20 degrees above the horizon. So 23 and a half degrees would be down there. Here's the sun on December 21st when you're in Altoard, Norway. Where is that? Below the horizon. Okay? If you were not seeing the sun then, you see this point over here now. None at all. It never comes up. Ever. Okay? So how many hours of daylight you got? 0. How many hours of darkness? Second? 24. It's also the land of the noonday darkness, okay, instead of the midnight sun. How about March 21st? What's the declination of the sun? 0, absolutely. Now on March 21st, you're right here, and Altoard, Norway is nighttime here. You don't see it, but it rises right about here. And it's up all day, doesn't go very high, and it sets right about there. You don't see it there, so guess what? 12 and 12. But let's see. Declination was 20. Let's go and draw it in here. Declination of the sun's right here. So you have 12 hours of darkness, 12 hours of daylight. Everywhere on the planet is equinox, equal day, equal night. Okay. Quito, Ecuador. Where is Quito, Ecuador? Anyone remember? Right on the equator. So, okay, where is the celestial? Okay, we draw ourselves. Got to take our coat off. Okay, and we're right on. Ooh, I erased the whole globe, didn't I? Okay, I need to erase that anyway. I think I've got enough. Let's take these off. Okay, and take this one off. Okay, one more ray of the sun. Okay. So, Quito, Ecuador. Here's the globe. That's the equator right underneath you. So guess where the celestial equator is? Right on your zenith. Celestial equator is right up there. You hear the sound effects? Okay. Right there. Okay. Now, you got on your bathing suit, I think, even there. Okay. Now, how many hours? What's the declination of the sun? You already put it? No, wait, you didn't put that. What's the declination of the sun on June 21st? 23 plus, no, June 21st plus, always plus. Yeah, plus north. 23.5 degrees north. But you're right on the equator, and what does the equator mean? Equal day, equal night, okay? Equator, they're all the same. Because you're on the equator, okay? Even when the sun's here, 23.5 degrees north right here, that's where it would be. So let's get Equator on the equator, right there. The sun's up here, the sun right here. You're on the equator. There's where the sun sets. There's where the sun rises. Halfway. You can't do any different from that. So guess how many hours of daylight when you're on the equator? 12 and 12. How about December 21st? December 21st, North Pole is pointing away from the sun. Okay, you're on the equator. Got to find it. There it is. It says it rises and it sets. The equator is over there at the time. Now the sun moves at noontime. It's north. You're in the summer months and it's south during the thing, but it still rises east and west. Okay, so it's 12 and 12 again. What was declination of the sun on December 21st in Quito, Ecuador? Negative 23 degrees, 30 minutes. But number of hours of daylight? 12, darkness 12. How about March 21st? What's declination of the sun? 0. How many hours of daylight and how many hours? 12 and 12. Now, there's now several,
They always have 12 and 12.
when you're on the equator. Actually, I was just going to tell this story. Probably been 2 or 3 years now. I was teaching this class. I had a woman, I think sat right over here, from Kenya. Fairly close to Nairobi, Kenya, I think, if I remember. I know she was from Kenya. Okay, where's Kenya? Right there. Okay? Right on the equator. Now, Nairobi is a little south of it, but she said she just grew up there. She always thought days were 12 hours and nights were 12 hours. Her whole life, that's all it was. And she came here to the U.S., where she's well above the equator, way up here. And then suddenly she had long days in the summer and short days at night, long nights in the winter and short nights in the summer. She said, it was the strangest thing. I always thought there were 12 hours of daylight and 12 hours of darkness. Because that's had been her whole life before she came here.
There goes the planet Earth.
Yeah, exactly. Right. Okay. So yeah, on the equator it's 12 and 12 and 12 and 12 and 12 and 12. All right.
That's a big thing on the internet. It's about flat earth.
Really? Okay, I hadn't seen that. I know there's a Flat Earth Society, but I didn't know what it really was.
Yeah, people that's just totally convinced that the earth
Was
is
it?
flat.
Really? I guess they've never been on a ship too far, have they? All right. Number 13. Has everybody filled out all three tables, every blank? All right. Number 13. Eratosthenes, who lived in the 2nd century BC, before Christ, was a Renaissance man before his time. The Renaissance came well after that, but he was. He was an astronomer, a geographer, a historian, a mathematician, and a poet. Okay? He could do it all. With such a diverse background, it is not surprising that he was director of the Great Library of Alexandria in Egypt. Okay? It doesn't say Egypt. He was Greek, but the Great Library was in Alexandria in Egypt, and that's Alexandria right there. Oh, there it is. Okay, I think. Yeah, that's it. On the Mediterranean, that was the center of learning from probably the 4th, 6th century BC up until probably 1st century BC. I mean, that was the greatest library in the world. He was director of that library. Okay? In one of the scrolls in the library, Eratosthenes read that at noon on June 21st, in the southern frontier outpost of Syene, Egypt. So you go down Egypt till you get down just about, Egypt's a little bigger today, but somewhere way down there, Syene, Egypt, okay? It said near the first cataract of the Nile. I'm not exactly sure what that means. I believe it's like a waterfall or something like that. Well, you know what they built there? Somewhere near that, they built the Aswan Dam. Has anyone ever heard of it? At the time it was built, it was probably close to being the largest dam ever built in the world. On the Nile River. Held water back behind it, which was there. They were also trying to control flooding because the Nile flooded, once or twice a year, it seemed like always, and they thought it was a bad thing, and so they were going to try to control the water. Also to produce hydroelectric power. Egypt didn't have a lot, so that was good. So it seemed like a very good thing. Except that there were some great historic documents and things that were put underwater. And some of them they had to move the whole building to get it above the water line. So that wasn't all that great. And then the other thing, why was the Nile Valley so fertile? Because of that flooding. The silt from upstream would flood, replenish the soil downstream, and it did that once or twice a year, and it kept now that they controlled the flooding, the land wore out. They could produce this many crops. Don't mess with Mother Nature. Okay, remember that commercial?
Okay. Now flow from the south to the north.
It's one of the few rivers that flows from the south to the north. Yeah, it starts in the mountains down here, actually near Kenya, in Tanzania. There's Lake Victoria right here. Is the border between Kenya. Kenya and Tanzania both share that as a border. Uganda is right there, and those are the three countries that surround Lake Victoria. Somewhere above that is the headwaters for the Nile, and then it comes out of that and heads through all of Sudan, does some wandering around, and then just after it crosses the Egyptian border, it starts getting flat. So right in there is where they built the Aswan Dam. We still had some gradient to it, but didn't have to do. It's just like you don't build a dam across, say, the Sahaba River somewhere way south of here, because it's flat. If you build a dam, everything gets flooded. when you build the dam, you put it where there's a good amount of drop off, and then it doesn't take as much concrete to build a dam. You can build it tall, the water backs up here, but it doesn't flood everything, just in the valleys. So wasn't the greatest idea. Gave them electricity, which is good. Okay, but on June 21st, in southern frontier outpost of Syene, Egypt, near the first cataract of the Nile, on noon the 21st, obelisk cast no shadow. You know, Egypt was famous for its obelisk. Think the Washington Monument. That's an obelisk in this country. Egypt had them all over. In Syene, they had an obelisk, no shadow at all. What does that mean? Where was the sun then? Directly overhead. So on June 21st, the sun was directly overhead. Okay? At noon, as noon approached, the shadows of the temple columns grew shorter and shorter. At noon, they were gone. Afternoon, they grew longer on the other side. Okay? Same type deal. Reportedly, a reflection of the sun could be seen at the bottom of the well. So here you had a well there. You look down, it was usually dark. At noon, you can see the sun down there because it's directly overhead. Got the idea? The sun's directly overhead on June 21st. Okay? On June 21st at Syene, the sun, this next one, was directly overhead. They said it about 15 different ways here. Okay? Where do you reckon, what do you think the latitude of Syene, Egypt is? June 21st, the sun was directly overhead. Okay? June 21st, the sun directly overhead. Right around here. 23.5 degrees north. What do we call that circle around the globe there? The Tropic of Capricorn. 23.5 degrees south. I said it back. Tropic of Cancer to the north, Tropic of Capricorn to the south. So anywhere in between those, you're in the tropics, meaning warm, sun's directly overhead once or twice a year. Okay?
Which one is that called? The Tropic of?
That's the Tropic of Cancer is in the north. Tropic of Capricorn in the south. But what they're asking for is to determine the latitude of Syene, and you said it right. What was it? 23 degrees, 30 minutes north. Exactly. Okay. That's number 13. That's really all it's asking. Okay, now we go back to where we live. Does anyone recall where we live? Okay, we know where we live, but okay. Oh, I erased the whole horizon. Okay, let me get the horizon back here again. Okay, here we are back in Bessemer, Alabama. We may not live here, but we'll do. Anyone remember what the latitude of Bessemer, Alabama is? You can try to see it there, but I've got an atlas back here of the state of Alabama. And it is exact. Bessemer, right near the middle of the book. Here's Bessemer. We'll just assume we're probably down here somewhere, but we'll take this line right here, come across here, and that is 33 degrees, 23 minutes, can't read, 45, I think it is. I've already said 40, yeah, that's 45. 33 degrees, 23 minutes, 45 seconds. Pretty precise, okay? So, it said, readjust the celestial globe to your latitude. Okay? It's about like that. Maybe I got it a little too much. So this is the equator here, and this angle here is 33 degrees north, 23 minutes north, 45 seconds from the equator. We're north of the equator. So that means on the celestial equator, here we do that as well. Does that look about a third? Needs to be a little bit more than a third. Is that enough? Need to go down a little? It's good. Okay. So we'll call this 33 degrees, and this is, by the way, celestial equator. 33 degrees, 23 minutes, 45 seconds. They probably don't need us to be that precise, but it's fun. Why not do it? Now, the question is, what range of declinations can stars have so that they never set? That is, they're always above the horizon. Can you name me one star that's always above our horizon all night long? North Star, of course. And how do we locate that North Star? On our celestial sphere here. Directly above what? Not on our zenith, no. Okay? We did it earlier, remember? 90 degrees from the, see, if this is 33, blah, 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 then the north, and this is not a very pretty globe down here. Let's see if I can clean up on that a little bit. I don't know if I can or not. Usually when I try to correct something, it gets worse. Okay, let's try this. Oh, that's not good. Okay, something like that. So it's got to be like this. That would be the North Pole. Now that should be 60-some degrees. No, 50-some degrees. I don't quite have it right. So here it would be something like that. Okay, so this is the North Star or Polaris. Okay, North Star. Okay, that's where it is. It's 90 degrees from the celestial equator, right? Due north from the celestial equator. All right. Now we know it never sets, right? Yeah.
The celestial equator is 33.
Okay. We are at latitude 33 degrees, 23 minutes, 45 seconds north of the real equator. That's our latitude. Now, I may not have this drawn well. I don't think I do. Okay. But that means our zenith is that same amount above the celestial equator, right? That's what we're standing here at that many degrees above the equator, so our zenith is that many degrees above the celestial equator. All right. Now, remember in that very first question we did, we determined that it's also the same, right? 33, 23, 45 would be how far above the horizon the North Star is, because that always gives you your latitude. Remember that first question? Go back a few pages. We did
I had trouble with that first question.
Oh.
I still haven't had time to look back at it.
Okay. If we're this many degrees north of the real equator on the Earth, that means our zenith is that many degrees above the celestial equator. That's where we are, you know.
So which one would you locate first? Let's say.
Okay. Well, if you know your latitude, you locate that first. Like when we did Altagar, Norway, we twisted this around till the equator was down here at 70 degrees. So that put that at 70, that put this at 20, you know, and you know, the celestial equator was there, the North Pole was 20 off here, you know, 70 north of here. Okay. North Star was on the North Pole, the North Star is directly overhead, right? The North Star is directly overhead. Stays there all night long. Okay. I don't stay there all night long, it's too cold. You know, the North Star does. Okay?
So from there we know my celestial equator would be 90 degrees, which would be the horizon.
I'll say that again.
From that, from knowing where my
Oh yeah, okay, you're absolutely right. If you're on the North Pole, North Star is directly overhead, your horizon is the equator. Okay, the celestial equator. All the way around. Exactly. Because you don't see. So you only see northern hemisphere things.
so right here investment, would I start with my zenith and then count down 33 and
Yeah, well, yeah, you start with the zenith, and this is 33, 23, 45 south of that, because we're north of the equator, so our zenith is north of the celestial equator, okay? Now, and then since this is 90 degrees here, that means this is the complement, the other half of that, which is really going to be 56, blah, 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 blah. And this is going to be 33, 23, 45. Because this is 90 degrees here too, the little angle is the same, okay? So, the question is, what range of declinations can stars have so that they never set? Well, declination is how far north of the celestial equator, right? How far north of the celestial equator would that be? Okay? Well, that can go up to 90. We know this one never sets. So basically, it's all the stars that are in this band here, and they go around the North Star, so that it's this 33 degrees, 23 minutes, and 45 seconds, this angle over here too. So let's do that. So this is 33 degrees, 23 minutes, 45 seconds. This is another one of those, 33 degrees, 23 minutes, 45 seconds. Okay, so any star that goes from here to here has a declination anywhere between this declination and 90 degrees, they will never set. They just go around the North Pole and never set. Right? So we got to figure out what the declination is there. Okay. Well, if we subtract the 33, 23, 45 from 90, that's going to give it to us. Doesn't that look like it? Okay, so let's do that. Except I'm not going to use 90. I'm going to use 89 degrees. I'm not going to use 60. I'm going to use 59 minutes. But here I'll use 60 seconds. Because that 60 seconds is 1 minute. That would make that 60. That would be 1 degree. That would make that 90. This will make the subtraction easier. I'm just lazy that way. Okay? And subtract from that, that's the North Star, and subtract the 33 degrees, 23 minutes, 45 seconds from that, and you'll have the minimum declination. That's the angle above the celestial equator. Okay? What will that be? 45 from 60 is? Second? No, it's 15. Subtract that, it's 15. 15 seconds. And then 23 from 59 is 36 minutes, right? Tell me I'm right. Okay. And this would be 56 degrees. So from that declination, north plus 56 degrees, 36 minutes, 15 seconds, up to 90 degrees. Any star within that declination, this declination, between this and that will be, those stars will never set. Does that make sense? So 56, 36, 15, plus, up to 90. That's the range of stars that never set. Declinations of stars that never set. For us, okay? When you go, like you said, further north, if you're right on the North Pole, then the North Star would be directly overhead. None of these would ever set from 0 to 90, and none of those set. But you come down a little ways, and more of them will set, more of them. If you're right on the equator, where celestial equator there, then everything sets. Well, the North Star doesn't, but everything else, right near the North Star, gone half the time, up half the time. Okay. So yeah, right on the equator, you see half the stars the first half of the night and half the stars the other half. Well, no, that's not quite right. You see half the stars, say pick a date, anytime during the year, and 6 months later you see the other half, and in between you see mixtures of those. Does that make sense? All right, now we're going to consider Mercury and Venus. Okay. I don't have the information to do this exactly, but what I'm going to do, I'm going to take it off what they gave me when I went to Birmingham Southern one of the times, I think it was the first time I went. It talks about Mercury and Venus, and it only gives us for September, October, November, and we're not in any of those. But which month do you think would be closest to us? September, October, November. Most like us now in May. Just pick one of these. September. Okay, we'll go with September. Okay? Now, here's what I want you to imagine. You want to be the sun again? Okay. You're the sun. Okay? We're here on the earth, and you're up, some part of the day. And let's see, right now we're about like this. Because you're up a little bit longer than normal. Okay. We go around you like this, all the way around the room. That's how big you're in the middle of the room. Venus is in between us and you. Okay, closer to us. So when you go down, you drag Venus with it. Okay? Because when you set, you'll still see Venus for a little while sometimes, other times you won't. Okay? Mercury is real close to you. You set, Mercury sets within usually minutes. Sometimes it's already set if it's on the other side. Okay? So you don't expect to see Mercury long. So let's see, we'll use the September of this year to approximate what it was doing. Okay? Venus is low at dawn near the east to southeast horizon. So let's start with Mercury. Let's use October for Mercury. When is Mercury visible in the dark sky? Okay? And it's either going to be just after sunset or just before sunrise. That's the only time you'll ever see it. And that would be, this doesn't make a lot of sense. It says it's visible below Jupiter for the second half of October. But it does say that that would be in the early morning. So just before sunrise. So we'll use that. Okay? When is Venus visible in the dark sky? Again, just before sunrise. But estimate how long each is visible on the dark sky. In other words, the sky, you can see the stars and stuff. Mercury will never be more than a few minutes, because when the sun goes down, Mercury being so close to the sun, it goes right down with it. So it won't be more than a few minutes. So that's all you have to put there. Venus, it may be up to a few hours. Not much, because once the sun's down, Venus also gets dragged down with it, and once the sun is set for very long. So I would say just a few hours at the most. So Mercury, few minutes, maybe up to 15 or 20, I don't know exact, but never an hour, I don't think. And Venus, it might be up there for a few hours, but not very many. Fewer than 6, for sure. Okay. Sometimes it's not even there. We'll just say that. That is the lab for the first chapter. Now, if you want to go home, take it home and ponder it and mull over it and fill in a few more things that you rushed through or something, you may have missed something, you want to go back and listen to it on the YouTube video, you certainly can. This lab is due a week from today. If you're finished with it now and want to get it off your hands, I'll take it now. So it's up to you. Give it to me today, give it to me on Thursday, or give it to me next Tuesday. Just get it to me soon. And are these the only people who are going to be in the class? Please get it back to me.
Number 15 and 16, just before Sunday.
Yeah, just before, yeah. It would be, both of those just before sunrise. It would be in the early morning hours, each of us. Now, I love to see Venus in the evening because in the morning, I'm rushing to get ready. I usually don't have time to go out and gaze at the stars. So I love it when it's in the evening. It's a bright display out there. But about half the time, you can't see it. If you were up in the morning, you'd be able to see it then. But you'll never see it both morning and evening on the same day. Okay? All right.
Don't you see Venus at night?
Yeah, you see it in the just after sunset sometimes, and just before sunrise sometimes. But you never see it past midnight. It'll sit before midnight. Just about always. Yes. Did we do number 11? I hope so, but maybe we did. 5, 6, 11. Oh, you're right. How did I did that? I do that often. Okay. Calculate the altitude of the sun in degrees above the southern. Okay. So here we are. We're on this. Okay, number 11. We forgot it. I forgot it. Okay. This is 40 degrees north. This is 40 degrees north. Okay? It says calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude 40 degrees. Okay? We don't really need this. That would just be approximating. We can do it with this. Sorry. Glad you caught that. Okay? Let's take off most of this. Woo! It didn't pick up my eraser. There we go. Okay. Okay. Not much of a change from what we had. We were at 33. Woo! I want to keep that. Okay. 33, 23, 45. Now we're just going to go to 40. So it's not going to be a lot different from what we had, but just a little bit. Okay. 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 Still an ugly globe. Okay. 40 degrees north. That's about New York City, Philadelphia, somewhere in there. Okay. We'll do that. That's probably a little too much, isn't it? Yeah, it's not too bad. We'll say this is the equator then. Here's our zenith. So this is going to be 40 degrees, just under half that. Not too far off from what we had before. So this is going to be 40 degrees here, and this is 40 degrees. So this is celestial equator. Okay. Now, answer me this. Yeah. Are you going to say something? Answer me this one. What is the sun's declination on June 21st? Say again?
0.
That's on March 21st. 23.5 degrees north plus, okay? So that means it's 23.5 degrees north. I didn't quite get it right. Let me try to get, oops, wrong. Okay. Let me try it one more time. Always my first one is my best line. About like that. That's probably a bit too much. The sun at noon on 21st of June is at 23 degrees 30 minutes north of the celestial equator, plus that, okay? So the question is, how far it is above the southern horizon at noon that day? Well, you need to tell me what this angle here is. This one here is 40 degrees. What would this one have to be? 50. And then this is 23.5 beyond 50. So what would that be? 73.5 degrees. 73.5 degrees. So that's the answer for number 11. Calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude plus 40. That would be plus 73 degrees 30 minutes. Okay? Repeat that procedure. This is number 12 for December 21st. What do we know about December 21st? Where's the sun? Okay, it's 23.5 degrees below. Whoa, that's strange. Below the, I don't know what was happening there. So it's 23.5 degrees below the celestial equator. So how far, this is the sun on 21 December when you're at 40 degrees north. So what would be its altitude above the southern horizon at noon? What would you do? I don't have the angles right here, but what did we say this was? This is 40, this is 50. Now, you're not at 50, you subtract 2330 from 50, right? So let's do, I'm not going to subtract it from 50, I'm going to subtract it from 49 degrees, 60 minutes. So 60 minutes is 1 degree, 1 plus 49 is 50. And subtract the 2330 from that, and what does that give me? 26 degrees, 30 minutes. So the sun is at noon, only gets up to 26 degrees, 30 minutes. When you're in New York City or Philly or whatever it is, it's at 40 degrees. Does that make sense? It's the altitude of the sun at noon. So noon in the summertime, way up there. That's why it's much warmer. It's up there longer, more direct radiation. In the wintertime, way down there. A full 27 degrees lower in the sky. Because of that difference. I mean, 47 degrees lower in the sky. So don't get nearly the direct radiation. Okay, did we get them all now? I think so. Okay, good deal. Any more questions about the lab? And again, remember, you can do a formula equation sheet if you haven't done one already for the test in chapter 14, which is coming up as soon as we finish. Can I go and take this off? Okay. Well, it's supposed to take off. There we go. All right. Okay. Now we're ready for chapter 15. Okay, now we need to go until 3 o'clock, and at 3 o'clock I stop, and you can take the test on chapter 14. Any questions on 14? Lab? Anything on 14? Okay. You need to do a little break? Let's do. I'll pause this. Okay, we started with the universe, okay? Now we're going to shrink down to the solar system. And the next chapter will be the Earth-Moon system, okay? So we'll get even smaller. So we'll start with the solar system. And this, by the way, I can't tell for sure because I don't have the book this came from. I think this is one of the far out planets, Neptune or Uranus, and this is a storm or something that's on that's been going on as long as we've been seeing the planet, which hasn't been all that long, but it's been multi-years. Okay. We're going to look at the solar system. Here's the core concept. In the new books, this is a little better than it used to be. They used to put it white print and a yellow background. Now it's a little better. It's white print and a sort of a tannish background. You can see it a little better. But the solar system is composed of, number one, the sun. That's where sol would come from. Sun. The sun, orbiting planets. Okay? Remind me at 2 o'clock I need to call roll again. Orbiting planets. Then we have some dwarf planets, not that many, but a few. And then small solar system bodies, and we'll talk about those separately. Now, this is a artist rendition of one way to look at the solar system. Let me tell you this, you'll never see it look like this. Ever. Okay? Because these planets, okay, and by the way, that's the sun. Now, if that were really the sun, it would be so big you could hardly see anything else. That space objects in perspective. The sun is so huge, the Earth is like a speck of rock or dust or pebble or something. So, the scale isn't right. The distances aren't right, okay? This is the Earth. Venus to Earth, that's not too bad. Mercury to Earth, not too bad. Mars to Earth, it's a little close. Then the asteroid belt, not too bad. Jupiter's way too close, and these others, we'll see later. You should be exponentially getting out there. They get further and further. In fact, the distance from, I want to say this right. I think the distance from the sun, that's hot. Okay, sun to the Mars is almost the same as the distance from Mars to the asteroid belt. Not quite. And then that is almost the same as the distance from asteroid belt to Jupiter is about the same as sun to asteroid. I mean, it almost is doubling, not quite, every time. I mean, so Saturn is not anywhere that close to Jupiter, and nor are these. They're way, way out there. Okay? So the scale's not right. Size, the planet scales are not bad size-wise, but the sun is way out of just. The scaling as distances are way off, but even more so, they never line up like this. Okay? Mercury's going around really fast. Venus goes around just dreadfully slowly. Earth goes around at a reasonable rate. Mars goes around at a reasonable rate. Jupiter goes around pretty fast, but it has such a long orbit, it takes a long time to get around there. Saturn even worse than these others. If they were this close, they would be, no way they ever line up like this. Ever. Ever. Okay. Now, the other features here that you can barely see, Earth has one satellite, that's our moon. Mars actually has two, and you can barely see them, but it does. Jupiter has so many they couldn't get them all on here. I think it's in the neighborhood of 50 to 70 moons, okay? Saturn has, I'd say, 30 to 50, probably not ever close to 50, maybe around 20 to 30, something like that. And these have, proportionally fewer. So they try to do a good job of representing those, okay? Now, when you were in grade school, how many planets did you learn there were? 9. How many are there now? Did we lose one?
Yes.
Well, actually not. It no longer is called a planet, it's called the dwarf planet. And so, way back, not too long ago, Pluto was considered a planet, now it's considered a dwarf planet. We didn't lose it, it just no longer is classified as a planet. Okay, so there's the core concept. So let's think about these things. Planets, moons, and other bodies in our solar system. The International Astronomical Union, the IAU, is the governing authority over naming these celestial bodies and classifying them, okay? The IAU defines what is a planet, what is a dwarf planet, and what are these other small solar system bodies and how they're divided up and stuff. In 2003, I guess all of you were alive then, right? Okay, barely. Okay. I was 52 years old then. Okay. In 2003, Pluto was redefined, taken off being a planet and redefined as a dwarf planet according to the IAU definition. It always was borderline, but they just said, you know, it just doesn't fit. And we'll mention several of those ways it doesn't fit. But we're not going to really talk that much about Pluto. If we get to go to the planetarium, the guy there a couple of trips ago really had a great presentation on Pluto. I never know what he's going to show, so I don't know what he's going to show this time. They're always good, though. But Pluto was under a fair amount of study not too many times ago. So he may talk about those. Now, let's start at the center, the solar system. Now, I want to read you a quote from the book, and later I'll notice another quote from the book. They seem like they're contradictory, okay? Let me make sure I can find it because this is a new edition. Okay, here it is. It's on page 379 if you have the new edition. It's the 4th paragraph from the beginning, not counting the overview. The sun has 700 times the mass of all the planets, all the moons, and all the minor members of the solar system together. So, when I said this picture wasn't to scale, I meant it. The sun is more than 700 times more massive than all these planets, all those moons, all the asteroids, and then all the comets and everything else that's in the solar system. Added together, the sun is more than 700 times more massive than all that. Everything else put together. So nowhere close is this the right size for the sun, because the sun is a big hot ball of gas, and these are stones here. You know, we are a lot denser than the sun, or somewhat denser than the sun. So that's why I said the scale is not right. Mass-wise, the sun has 700 times the mass of everything else put together. Now later there'll be another statement that you have to interpret, but remember that. Okay, we have now 8 planets. Used to be 9, but now it's 8. On the order of 100 moons. And like I said, the biggest number is around Jupiter. I think that's between the 30 and 50 range. And then Saturn has probably 20 to 30. And the other big planets out there, gas giants, we'll talk about those in a minute, have quite a few. There are thousands of asteroids. That's between Mars and Jupiter, a belt there, the asteroids. And literally millions of icy bodies. Some of those are comets and other things like that. Okay? Millions of those. Now, for a few things, you might be able to measure in miles when you talk about our solar system. Generally, miles are way too small. For instance, from us to the sun, 93 million miles, okay? Us to the moon, several 100,000 miles, okay? It's just such big numbers. So they use a more convenient unit, which is a lot bigger unit, but that keeps the number smaller. And that unit is called an astronomical unit. And good old us, we think of ourselves as being so important. That is the average Earth to Sun distance. In other words, that's about 93 million miles. One astronomical unit. So everything else will be measured, or sometimes is referenced to those astronomical units. Now that distance is about 1.5 times 10 to the 8th kilometers. Are y'all familiar with scientific notation? That would be 1, 5, 0, comma, 0, 0, 0, comma, 0, 0, 0 kilometers, okay? 150 million kilometers, okay? 150 million kilometers, which is about 93 million miles. Now, planets are classified by size, density, and atmospheres, okay? Size, densities, and atmospheres. And by classifying them in this way, you fall into two groups, okay? This is by size, density, and in many ways atmosphere as well, but atmosphere is quite. But mostly size and density. You have the four closest planets, and they're also the smallest planets: Mercury, Venus, Earth, and Mars. These are, it says by size and density, they're fairly small, and they're mostly rocky materials. Mostly metallic nickel and iron. Now they have that backwards. It should say iron and nickel. And you might say, wait a minute, the Earth isn't mostly iron. Yes, it is. On the surface of the Earth, there's only a lot of iron in select places, Birmingham, Bessemer being one, Pittsburgh being another, Birmingham, England. You know, there's a lot of places where there's a lot of iron ore, or a fair amount of iron ore near the surface. But guess what? If you go deep enough into the Earth, you run into almost majority iron with some appreciable amount of nickel. There's not that much nickel on the surface, but there's way more nickel deep down than there is anything else that occurs on the surface. We'll talk about that in a later chapter, okay? These are the terrestrial planets, meaning rocky, okay? Remember the old show, Third Rock from the Sun, okay? That pretty much describes us. Now, they're not mentioning it here, but then there's a band of asteroids, okay? We'll talk about them later, but some people think that should have been another planet there, okay? But they blame it on Jupiter. Jupiter was just too big, too strong a gravitational field, and it kept that planet from forming. So the outer planets, the ones that are beyond the asteroid belt, Jupiter, Saturn, Uranus, and Neptune, these are called, now this is just calling them the giant planet. Most of the time I see that referred to as the gas giants. Whereas these are solid rocky materials, these four, these are not. These are gaseous. Now, some of them are so cold that the gases have actually frozen or maybe liquefied or frozen, but they're mostly gases. Mostly hydrogen, helium, methane, which here on the Earth would never, ever be in liquid or solid form. Some of them are so cold, you start having some liquid hydrogen. I doubt if you ever have liquid helium, and could have some liquid methane, okay? So those are the gas giants. They are balls of gases, not balls of solid material, okay? Pluto, no longer considered a planet. I'll give you a few reasons right now why. Later we'll do some others, okay? Number one, size. Like I said, the inner four are small, the outer four are huge, giants. Pluto, much smaller than the smallest of these. It just doesn't fit. It's way out there, and yet it's not a gas giant. It's more rocky material, icy material, but it just doesn't fit. It doesn't fit the pattern of small being close, large being outside, because Pluto is smaller than even, in fact, Pluto is smaller than our moon, smaller than several moons in the solar system, okay? Number two, density. Same type thing. These are dense planets. These, because they're gas, they're not as dense. Pluto is dense again, so it doesn't fit there either. And like I said, the atmosphere is, now there's several other reasons Pluto doesn't fit. We'll talk about some of those a little bit later. Okay? Any questions? All right. The order of the planets, here's this fictitious slide again. And here's what they are. Okay? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto is somewhere out here, actually smaller than Mercury. I'm pretty sure smaller than our moon. I'm definitely sure it's smaller than some of the moons of Jupiter and Saturn. It just doesn't fit with the other planets. Terrestrial, gas giants, kind of terrestrial again. It just doesn't fit. Okay? I don't know why they had this one in here. And never do they line up like this, and these scale on distances are way, 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 way off. Okay? They should be stringing way out there from here on. We'll see that a little bit later. Okay? The picture in the book actually shows a lot more, and I don't know how many of you have the new book. Do most of you? Oh, super. The picture in the book that's sort of equivalent to this, the sun probably still is not scaled quite right, but it's a lot closer than this one is. Mercury, and again, they don't line up this way. Mercury, Venus, Earth, and Mars, again, the distances aren't right. They just sort of evenly spaced them. And then you have the asteroid belt, and in the picture in the book, they list Ceres, that's C-E-R-E-S. It's one of the larger asteroids that you have there, okay? It's considered to be a dwarf planet, even though it's in the asteroid belt, okay? Then you have Jupiter, Saturn, Uranus, Neptune, and then Pluto is shown here with one moon, and Pluto is small, and you see again, now this is more to scale. Pluto, you see how small that is compared to Mercury, which is the next smallest planet, and it's just tiny. If they had put our moon correctly, it would be bigger than Pluto. They don't show any of the moons around Jupiter or Saturn. Several of those are bigger than Pluto. But Pluto has a moon that's almost as big as Pluto. So that's really almost a binary system that does like this. Then they list several others. Haumea, Makemake, Eris are all other dwarf planets. So you see in this figure, that's not in this one, the 5 major dwarf planets. Ceres in the asteroid belt, Pluto, Haumea, Makemake, inside the Kuiper belt, or Kuiper belt, Kuiper I guess is how you say it, and Aries just on the outside of the Kuiper belt, okay? And then it shows one little comet. The comets are in the Kuiper belt, and every now and then one will take off and go toward the sun and go back out. Okay. There is an example here. Let's just take a quick look at it. How long would it take to travel the average distance between the sun and Earth in a typical jet airplane speed of 1,000 kilometers per hour using equations from section 2.2? Now, we haven't done 2.2. That's why I sort of skipped these things. But if you notice what it said before here, average of 1.5 times 10 to the 8th kilometers. Okay, it's going 1,000 kilometers per hour. 1 hour would get you, well, here's the other way to look at this. I said this was 150 million kilometers. That's 150,000 kilometers. So it would take 150,000 years. Hours. 150,000 hours. Divide that by 24. Keep going down. You get how many days. Divide that by 365. You'd have how many years? It would be a long time. A long, long time. 1,500 hours divided by 24 hours a week, about 62 days. Okay, about 2 months of traveling in a jet. If you could do it, you couldn't, to get from here to the sun. You wouldn't want to. The jet would melt. Okay, but that's beside the point. Interplanetary space probes travel about 73 kilometers per second. How far could they travel in a year? So multiply that by 60, multiply that gives you minutes. Multiply that by 60 again, that gives you an hour. Multiply that by 24, you get a day. Multiply that by 365, and you get the days in a year. That's about 2.3 times 10 to the 8 kilometers. That's how far they would travel in a year, which is still just a little bit further, not quite one round trip to the sun and back. Wow. Okay. Now, we're going to start looking at the planets one by one. In your text, however, you'll notice there's a table there. I found this table extraordinarily enlightening. Now, on the slide set, they're going to show the table at the end. In the text, it shows at the beginning. I think we ought to take a quick look at the beginning. That's where it is in the text, and let's go. So, what we're looking at first is the average distance from the sun, and it first gives it in millions of kilometers, which I don't relate to very well, but also in astronomical units. Astronomical unit would be the distance from Earth to Sun. So, if you look at Mercury, that's approximately 3/8 of the distance. You got the Sun here, Earth here, about 3/8 of the distance, less than half, more than a quarter, more than a third. That's where Mercury is. Okay, 3/8 of an astronomical unit. Venus, almost 3/4 of an astronomical unit. So it's only 2.28, a little over a quarter of astronomical unit from us. That's our closest planetary neighbor. Okay? Then Earth is, of course, one astronomical unit, because that's how we define it. Distance from Earth to Sun. Mars, okay? So here you have the Sun. Okay? Let's take that being the Earth. Sun somewhere over here. Mercury, about 3/8, less than halfway. Venus, not quite 3/4 of the way from the Sun to the Earth. Mars, okay, if you take half the distance between the Sun and the Earth, add it to that, that's how far Mars is. Much further from us. It's half an astronomical unit away. Venus is just a little bit more, a quarter of an astronomical unit. So it's almost twice as far away as Venus is. Okay? So, look at the big jump when you get to Jupiter. Mars, 1.5 astronomical units from the Sun, not from us, from the Sun. Okay? The asteroid belt would be about 3 astronomical units, so it's almost double. Then you almost double again to get to Jupiter. Okay? So in other words, it's more than 3 times as far from the Sun as Mars is. Let's go back to this picture. If this was correct, and that was the distance from Earth, from the Sun to Mars, then 1, 2, 3, somewhere out here should be Jupiter, not here. Okay, that's what I said. The scale is very, very off here, but they're just trying to show a picture. The sizes aren't bad, but the scale of the distances is pretty awful. Okay, and then you look at Saturn, almost double what Jupiter is from the Sun. 5.2 is from the Sun to Jupiter, astronomical units, 9.5. Okay, almost double. Okay, Then Saturn to Uranus, more than doubled, okay? So they almost double every time. Nowhere close to what this picture is. And then Uranus to Neptune is not quite doubling, but it's in that neighborhood, okay? Amazing, okay? So basically, if this were true, this was one astronomical unit, then Neptune would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30 of those astronomical units before you would get to Neptune. It's way out there, folks. Way, 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 way out there. Okay. So even the picture in the book, which has a little more distance, is nowhere close to being the right distance scale, because you just wouldn't be able to see them all on the same picture. You'd have to have a page this wide, to get them all on there. Okay, so that's distances. Amazing distance. Inclination to the ecliptic. Now, the ecliptic is considered to be the plane that connects the sun and the earth. That plane. Now, Mercury, about 7 degrees off the plane. 7, okay? Now, it's so close to the sun, it's not far off, but because it's so close, the degrees are pretty large, 7 degrees off. Venus, about 3.4 degrees off. Earth, right on that, because that's how we define the ecliptic. Mars, 1.9 degrees. Jupiter, 1.3. Saturn, 2.5. Uranus, 0.8. And Neptune, 1.8. Okay? They're all less than 10 degrees. And if you exclude Mercury, which is so close, they're all less than 3 degrees off. No, I'm sorry, except Venus. All less than 4. Venus is so close, exclude it, and everything else is less than 3 degrees. Considerably less than 3 degrees. Okay? So we're all in just about the same plane. I mean, there's some variation. They're off a little bit, but not bad. If you had to include Pluto on here, 15 degrees off. And it's so far out there, it's just not in the same ballpark. I mean, it's just not, it doesn't fit the other planets. Now, I'm guessing on that 15. It seems like I remember reading that somewhere. Okay? Now, let's look at the orbital periods. Now, what you expect is the planets closest to the sun to go a little faster, because they don't have as far to go, okay? And to get longer as you go further out. This is orbital period in Earth years around the sun, to make one complete orbit around the sun. Notice Mercury, about a quarter of a year, okay? Venus, about 2/3 of a year, 3/5 of a year. Of course, Earth is 1 year. Mars is about close to 2 years, okay? Not quite, but close. Jupiter, close to 12 years. But it's so far out there, no wonder it takes so long, okay? Saturn, almost 30 years. Uranus, 84 years to go around once. These are Earth years. And Neptune, 165 approximately years to make one trip around the sun. So you see, they never line up. They're just going different speeds, and there's so much distance between. So now let's look at the rotation period. That's how long a day is, you might say. Well, Mercury, it takes a quarter of a year for it to go around the sun. It takes almost 2 months for it to spin one time. Okay, so it's a real slow spinner. So it takes about 2 months for it to spin, about 3 months for it to go around. So it's about 1.5 days per year, okay? Because it only spends a little bit of time so it's rather strange. But look at Venus's. It spins more slowly than it rotates around the sun, or revolves around the sun. It takes, what is that? I said less than 2/3 of 12 would be 9, isn't it? No, it's 8. It takes a little bit, between 7 and 8 months for it to go around the sun. It takes almost a year for it to spin one time. And what's more, look at the sign there. Venus spins backwards. So not only is it spinning slowly, it's spinning the wrong direction slowly. Okay. So on Venus, the sun rises on the west, and one of Venus's years later, a little bit longer than that, it sets in the east. Okay. So really, really bizarre. Now, there is speculation of why that's true. They think that early, and we're going to talk about this either in this chapter or next chapter, the formation of the solar system. In the early years, there was a lot of junk going on out there. The sun was still not stable yet. There were explosions. Stuff was flying around through the solar system like crazy. And they think that Venus had a collision with some of that other stuff, a pretty major collision that basically knocked it so it made it spin backwards, slowly but backwards. So Venus's year is shorter than Venus's day. Okay, strange but true. And of course, on Earth, a year is 1 year, okay? And a rotation period is just under 24 hours. Okay, Mars, look at that. Its year is about close to 2 years, Earth years, but its day is very close to ours, a little more than 24 and a half hours. Okay, Jupiter, its orbital period is about almost 12 years. Earth years, but its rotation is only 9 hours. So what takes us 24 hours to spin, Jupiter is this huge, huge planet. It spins in just 9 hours. So its surface is flying around, even though its thing around the sun is 12 years. So it takes a lot of days to make a Jupiter year, Jupiter days to make a Jupiter year. Saturn spins awfully fast too, only 10 hours to make one rotation, but about 30 years to make one Saturn year. 30 Earth years to make one Saturn year. Uranus, another strange one, spins backward too. But it's not nearly as long, about 17 hours to make one rotation in the wrong direction. Now here's something else about Uranus. It's rather strange. Most of the planets, the axes are not straight up and down compared to the ecliptic of the sun. They're at a little angle. Ours is what, 23.5 degrees. Most of the others have some tilt to them, okay? Uranus almost is sitting whose axis is in the plane, okay? So how can you tell which way is turning positive and negative, because its axis is very close to the plane. So it's a really weird, I don't know what it would be like to live there. Of course, it's so cold that nothing could live there. So it does spin backwards. Venus and Uranus spin backwards. Venus takes about 243 days to spin one time. Uranus only about 17 hours. So it's spinning faster than we are, but it's going backwards. Neptune, about 16 hours, but forward. Okay, the correct direction. Okay, let's look at masses. Now we'll count the Earth mass as 1, and this is just, Mercury is 1/20th the mass of the Earth. Mercury is just barely bigger than our moon, more massive than our moon. So it's the smallest planet. We'll get to that in just a second. Venus is almost the size of the Earth, 4/5 the size of the Earth, mass-wise. Actually, diameter-wise, it's even closer, but mass-wise, it's the closest to us. It's really closest to being our twin. It's not a very good twin, but it's pretty close. Of course, our mass is 1 Earth mass. Mars, only about 0.11. Okay, so it's about a tenth of as massive as the Earth, more than twice as massive as Mercury, but those are the terrestrials. Notice how small those masses are, from 0.05 to 1 Earth mass. When you get out to the giants, Jupiter is 318 times more massive than the Earth is. You could fit, mass-wise, 318 Earths inside Jupiter. It's amazing. It's one huge planet. Mass-wise, Saturn is 95 times more massive than the Earth. That would be impressive, except it's not nearly 318. Uranus and Neptune, again, talk about twins. You know, they're almost the same rotation period. So many things about them are similar. Okay, their masses, Uranus is almost 15 times the mass of the Earth. Neptune is a little over 17 times. Okay, now that's just mass, how much of it there is. If you talk about size, as in spatial size, if you count Earth radius as 1 again, Mercury is a little bit better than a third, okay, the size of the Earth, size-wise. Whereas Venus is 95%. I mean, that's almost the same size as the Earth. The Earth is exactly 1. Mars, about half the size of the Earth, a little bit more than half. Jupiter, radius-wise, even though its mass is 318 times, its radius is 11 times. But remember, if you did the total volume, the volume is 4/3 pi r cubed. So cube that radius, cube 11, that's 11 times 11 times 11, that's a good deal more than 1,000, and then multiply it by 4/3 pi, which is about another factor of 4. Okay. Saturn, even though its mass is so small, is much smaller than Jupiter, its radius is pretty close to Jupiter, which means Saturn is not very dense. And Uranus and Neptune, look at that, twins again, for their radii or diameter almost exactly the same, 4 times that of Earth. Atmosphere, okay? Remember, that was one of the ways we classify planets. Size, density, and atmosphere. We haven't got density yet. Let's look at atmospheres. Okay. Poor old Mercury. Almost no atmosphere at all. We say none. In many ways, it's a lot like our moon. Our moon has no atmosphere, and actually Mercury's just a little bit larger than the moon. They are very similar, except Mercury's a lot hotter. Okay. So keep that in mind. We'll talk about that in a minute. Oh, I'm sorry, I skipped density. Let's go back and see density. Glance at the table. What is the densest planet? Say again? Glance at the table. Earth. Not by a lot, but it is the densest planet. Amazing. Next most dense is Mercury, not far behind Earth, and then Venus, not far behind Mercury. And Mars is, lagging a little bit, but still more than half. Look at those compared to those giants. None of them are close. They're gases. They're much lighter. The density is less. Jupiter 1.33 compared to, say, Mars, which is almost 4. Earth, which is more than 5.5. And then Uranus 1.29 and Neptune 1.64. But look at Saturn, the least dense of the planets. Do you know what that means for it to have a density of 0.69? That's less dense than water. If you had a big enough tub of water, Saturn would float. None of the rest of them would, because water's density is 1. So anything denser than water would sink, anything less dense would float. Saturn is so light, not light, so low density, it would actually float in a pool of water. You just don't have pools of water that big. the water would freeze immediately anyway. Never mind. So let's go back to atmospheres. Mercury has absolutely no atmosphere, or none, not to speak of. Venus, look at Venus and Mars. Mostly carbon dioxide. No. What have you heard about carbon dioxide in the atmosphere? What does that create or cause, or what problems does that bring up? Carbon dioxide in an atmosphere? It's a greenhouse gas. It tends to trap heat. That's why they worry that we may be warming the planet because of our activities, as in fossil fuel consumption, and putting too much carbon dioxide in the atmosphere. Even though it's not very much, but compared to what it should be or has been in the past, it's gone way up since the Industrial Revolution and keeps climbing. And our temperatures, they fluctuate over time. They always have. We've had ice ages and very warm periods in between. But since the Industrial Revolution, temperatures are going up more quickly than you would think would be happening because of just natural fluctuation. That's why they call it global warming. Some people argue it's not happening. Say again? Somewhat.
Some say it's a hoax.
Yeah, some say it's a hoax. Some have said it's actually a Chinese hoax, but we won't go there either. But Venus, being so close to the sun and having a very dense, high carbon dioxide atmosphere, it is one hot planet. In fact, it's hotter than Mercury is. Now, Mercury, with no atmosphere, the side that faces the sun is burning hot. The side away from the sun is freezing cold because it has no atmosphere to balance out. Venus, on the other hand, with that heavy, dense, high carbon dioxide atmosphere, it's just uniformly hot. Its average temperature is higher than that of Mercury, but its extremes are not nearly as much. It never cools off. And remember, it turns so slowly, you don't get much difference day, night, or whatever. Everything stays really, 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 really hot. You couldn't support life there. Okay? Now, how is it? Venus, carbon dioxide, Mars, carbon dioxide. In between, Earth. Its atmosphere is mostly nitrogen. Second most is oxygen. This just doesn't seem to fit. Okay? Thank you very much. If it weren't for that, no life here. Okay? Life does not exist on a high carbon dioxide atmosphere. It can't breathe. Okay? So none of the other planets, look at them, have the amount of nitrogen, the percentage nitrogen we do. Close to 80%, it's like 78% of our atmosphere is nitrogen. Whereas the nitrogen in the other planets, why did the Earth get it all? Not all, but huge amounts of nitrogen. I think we were meant to live here, I don't know. It's just, it is pretty amazing. Now, there is a reason that we have high concentration of oxygen. And you know what that reason is? Look out the window. What you see? Green plants. Green plants take carbon dioxide in and breathe out oxygen. Okay? If it weren't for the green plants covering the surface of the earth, we would not have oxygen in such high amount. So therefore, without them, we're not here. They came first and provided an atmosphere that we could live in, basically. Now, if we cut down or mow down or build too many houses and roads and pave over too much of the land mass, and we cut down too many of the oxygen-producing green trees, which, by the way, is happening in equatorial areas. Have you ever heard of a tropical rainforest? most of the oxygen produced on the planet is coming from those tropical rainforests. But a lot of countries that have them in it, they're saying, hey, we got the warm temperatures, we got moisture, this is pretty good soil here, let's cut down these things. And literally what they do when they cut them down, they can't use all the wood, they burn huge amounts of wood. Carbon dioxide going into the atmosphere. That, in addition to burning coal and fossil fuels, that's contributing to CO2 too. And a lot of countries are doing it. We aren't, but a lot of countries are. We don't have that many. We don't have any tropical rainforests to speak of. But they are cutting them down so they can plant soybeans and corn, and these crops. The sad news is the tropical rainforests keep the soil because they feed leaves and things back into it. Once you remove them, and then you're growing crops, you're harvesting the crops, very little is going back into the soil. The soils degrade quickly and soon turn into really unproductive soils. Okay? They were doing great when the tropical rainforests were there, what should have been there, mixing with the soils, having a lot of humus, organic matter in it. They were sustaining themselves quite nicely until we cut them down, burned the residue, and then started planting crops. We use up that organic matter, and then it becomes very untillable soil. And now there's nothing producing that oxygen that the tropical rainforests were. No crops, nothing else. We are being really stupid. I mean, we, the human race, when we do that. Get off of that. Okay. We're the only planet with high nitrogen and high oxygen. That's why there's life here. Then you get out to the gas giants and look how similar they are. Hydrogen, helium, hydrogen, helium, hydrogen, helium, methane, hydrogen, helium, methane. Okay? There's methane in the Jupiter and Saturn too, but it's just higher. Hydrogen, helium. Now, where does hydrogen and helium come from? Where have we run into hydrogen and helium before? As in last chapter. That's what most stars start out. They start out mostly hydrogen. Once it starts the fusion process, the hydrogen fuses the helium. That's the process that makes a star. Okay? So, and again, this is jumping ahead, when the sun was trying to figure out and become the sun, it was having explosions that blew air out, probably blew all the atmosphere off of Mercury. Mercury was just way too close. Okay? The others, us and Venus and Mars, we got the CO2, the oxygen, and we got nitrogen. The gas giants, they got those light gases got blown way out there, and that's what they're mostly, hydrogen and helium, with some methane. And by the way, methane is another greenhouse gas, but they're so far out there, it's not going to make any difference. Now, solar energy received, this is strictly a function of how close you are to the sun. Mercury gets the most because it's so close, 13.4. This is in calories per square centimeter per second. Venus, 3.8. Earth, 2.0. Mars, 0.86. Jupiter, 0.08. Saturn, 0.02. Uranus, 0.006. And Neptune, 0.002. Notice, the further out you go, the less solar radiation you get. They're just that far away. Solar radiation drops off as the inverse square law, meaning the further you are, square that, and that's how much it's reduced. So that follows directly by how far they are. Okay, that's the table. We'll repeat some of that as we go, but let's look at the planets. Okay, let's start with Mercury. As we said before, the innermost planet. About 3.38.4, 2/5 of an astronomical unit from the sun. So it's closer to the sun than it is to Earth. It'll be about 0.6 from the Earth, 0.4 from the sun. It's a highly elliptical orbit. Now, what do we mean by that? A circular orbit would mean, now I want to use the Earth as if it's the sun, that you're always constant distance from the sun. None of the planets are circular orbits. One or two are pretty close. None of them are exact. We're all in what we call an elliptical orbit. Sometimes we're close to the sun, and sometimes we're further away. Now that's a huge exaggeration. Usually it's not much, just a little bit difference. Mercury has one of the highest elliptical orbits. Real close sometimes and a bit further away others. The extreme of that action, that's your comets. The comets start way out there, and every now and then, every 100 years, hundreds of thousands of years or something, they come and get real close to the sun and then go way back. They are very elliptical. Okay? Guess what? Pluto would put Mercury to shame. Sometimes Pluto is inside where Neptune is. And sometimes it's way out. It's a so another reason it's a dwarf planet, not a planet. Among the 8 planets, Mercury is highly elliptical. If Pluto were included like it used to be, Mercury would be negligible compared to what Pluto is. We've already said average distance 0.8, orbital period about 3 months, rotational period about 2 months. Okay, goes around the sun in 3 months and spins once every 2 months. So has about 1.5 days a year, each year. Okay, rather strange. And it's, like we said at the end of the lab, visible only shortly after sunset or shortly before sunrise, if it's visible at all. In fact, I'm not sure I've ever seen Mercury because it's just a tiny little speck. It's a very small thing, and it's a tiny little speck just before the sun goes up or right after the sun sets, and there's still enough light in the sky you can barely see Mercury. So if you can see it, and most of the time you can't, it's only going to be for a number of minutes. Highly cratered. Semicolon, no atmosphere. Those are interrelated. What does your atmosphere do for you? Things that are coming in to crash into the planet, they slow them down, burn them up. In fact, what do we call, when space junk comes into our atmosphere, what do we call that? There's 2 common names for it. Say again?
Meteors.
Okay, there's the technical name. They're meteors when they enter our atmosphere. They're meteorites if they make it all the way to the planet. Shooting stars or falling stars. There's a common name for them. Guess what? Coral, Mercury with no atmosphere, they just crash into the planet. Crash into the planet. Crash into the planet. That's why it's highly cratered. And that may be why it has such a highly elliptical orbit. It may have really had some really serious crashes in its early thing. It is pretty much by far the smallest planet. But mass-wise and volume-wise, the smallest planet. If you included Pluto is much smaller, okay? So once Pluto was out, Mercury became the smallest planet, okay? Here is the sort of the rendition of why Mercury is so hard to see. Mercury goes around the sun inside of where we are, okay? Now, when Mercury is closest to us, its face is facing the sun, we only get a little glimpse of Mercury. That would be like a crescent Mercury, okay? So when it would be closest to us, you'd think it would be easiest to see. No, it isn't, because all we see is the dark side of it. So we don't see it at all. You just see a little sliver of it. When it's next closest to us, you still only see about half of it. When you get a full Mercury, it's farther from us. It's on the other side of the sun. And yet at least half of the time, it's already below the horizon when you would be able to see it. When the sun drops down, it's already dropped down beforehand, so you'd never see it. So only when the sun goes all the way down beneath the earth, or before it comes up here, depending on whether it's morning or evening, you would sometimes, occasionally see a Mercury there. Once this is below the horizon, you might be able to see that Mercury. But guess what? It's still in a pretty light sky, even though the sun's not up yet, or it's already set. It's so hard to see. This would be hard to see. That would be pretty hard to see. These down here, you can't see at all. Okay, so that's why when you can see Mercury, if you can see it, it's only going to be for a number of minutes, because once the sun goes down, Mercury goes with it. Or before the sun comes up, Mercury may precede it up, and you see it short time. Once the sun gets up, leaves it out. You don't see anything. You don't see any stars. You don't see anything. Occasionally you'll see our moon, but you're not going to see any planet after the sun's up. Make sense? All right. Here is a picture of Mercury. Now this is a composite of several different shots of Mercury, but you can see how heavily cratered it is because it has almost no atmosphere. If it had an atmosphere, you would see a fuzziness around it. No fuzziness, stark. So craters all over the place. All over the place. Poor old Mercury just gets bombarded. Because these comets that come in, as they get closer to the sun, we'll talk about them later, they start melting, giving off dust and particles and rocks and stuff. Mercury passes through the path of that, it gets hit by all that stuff. Okay. So, pitted, heavily cratered, no atmosphere planet. Make sense? Let's move on to Venus. Okay, and by the way, nothing replaces reading the book, okay? There's a lot more said in the book than I can possibly say here. So, let's look at Venus. Its orbital distance is 7/10, okay? I was saying, what did we say before? 0.72 it says here. I was saying about 3/4. This is closer to 7/10 of an astronomical unit from the sun, which means it's 3/10 from us. So it's less than half the distance between us and the sun. So it's the closest, except for our moon, the closest heavenly body to us. That's why, except for the moon, the sun and the moon, it's the brightest thing out there. It's not a star. It's often called the morning or evening star because that's when you see it. It comes up either before the sun comes up and it's really bright, or after the sun sets, you see it and it's really bright. About half the time is in the morning, and about half the time it's in the evening, and when you see it, it's brilliant. It's so pretty. And it's called the morning and evening star. The brightest thing in the sky, but only is there for at most a few hours. Just like we saw with Mercury, it exhibits phases too. You almost need binoculars or a telescope to see those phases. But you'll see half of Venus sometimes, a full Venus, and a new Venus, crescent Venus, various things like that. So you do see phases. So sometimes it's brighter than others. Okay. This is the strangest thing about it. Its rotational motion is opposite to the orbital motion. So if it's going around the sun like this, it's spinning like that. Okay. Rather strange. Only it and Uranus do that, but it does it very much more slowly than Uranus does. Okay? The Venetian day, the time it takes to spin once, about 246 Earth days, is longer than the Venetian year, which is how long it takes to go around the sun, which is about, what was that? 2 or 3 months. What was it? I don't remember exactly. It's about 9 months. No, yeah, closer, 8 or 9 months. And yet it takes well longer than that for it to spin once. Backwards, okay. Now, since it is the closest planet to us, we have sent up numerous probes there. Okay? Now, most of those, I'm going to hazard a guess here, most of those don't make it to the surface and still send us much information. A Few of them, I think, have, but most of the time it's just stuff from outside. Why? It's so stinking hot. Things will operate well then. And number two, we mentioned carbon dioxide in the atmosphere, a lot of that. Other things in the atmosphere, sulfuric acid. You know, it is not a nice place to be. Most of our equipment would probably, if it didn't burn up, it would corrode away very quickly. Okay? But it has been visited by numerous probes, so we have a fair amount of information about it. Mostly carbon dioxide in the atmosphere, extraordinarily high temperatures, but also it's a very dense atmosphere, so it's very high pressure. So the atmospheric pressure on Venus would be greater than probably any of the other planets. Okay, can't say that for sure, but I would pretty good guess. The surface is mostly flat but varied. Guess what? Varied through a few meteors make their way through that atmosphere. It's so hot to begin with, such a dense atmosphere, they're going to burn up long before they ever make it to the surface. So it is a pretty flat surface, but it does have variations in it. I think they're going to show a picture of that. Well, no. First thing they're going to show is these numerous probes that have been sent. Now this only goes to 89. I think a few more have gone since then. But they started as early as 61. Now, I just wanted you to notice who has sent more things to Venus. Just looking at the country here, the owner. USSR, Soviet Union. That's why it stops here, because Soviet Union fell apart somewhere in there. Okay? They have, Russia Federation has still sent some, and also not included in this table are any EU, European Union, space agency. And in fact, I think China has now sent a few. I don't know if they made it to Venus yet. So a few other countries are getting in on the act, or organizations are. But USSR decided to focus on Venus, so we decided to focus on Mars. Okay, so when you see Mars, you'll see US outdoes USSR. Even though it's further away, we found it more interesting to look at. Now, most of these you'll see are flybys. A few of these impacted Venus, meaning they crashed onto the surface. Well, that means crashed on, this is impacted, it's almost the same thing. This one, some of these actually landed, but I can't swear to you, because I don't know USSR history, how much good data they got from there after they landed. Number one, it would be a pretty rough thing. It's so hot, such a dense atmosphere, and so inhospitable atmosphere. Okay, and here we have landers and orbiters there. Orbital views. So you see all these things. In later years, more and more became landers, and it said they sent photos from the surface. And again, these are mostly USSR. Others flew around and radar mapped it. They sent probes into it. And a lot of photos. See, the U.S. started picking up more here. Okay, so there's the visits to Venus. Here is probably from some of those Russian landings or near landings, approaches to the surface. They show here, and this I know is in the old book, I don't think it's in the new book anymore. But now they've added some color here, but more than likely, if my understanding is right, these are lava flows. Okay? When you have a volcanic eruption, I think this is supposed to be a volcano on the surface of Venus, and it's a pretty massive one. That doesn't cool very rapidly. So the lava flows for a lot longer time, and this could be lava flow here too, just beginning to solidify. But it is incredibly hot on vacation there. Okay, but when they say mostly flat but varied, there are some mountains, there are some valleys and things like this. Most things that would be solid on Earth will liquefy somewhat on Venus. Some things that would be liquid on Earth would be vapor on Venus. Not a good place at all. Okay. Now, before we go to Mars, there are a couple more examples here. How many times would a space probe on Venus' surfaces have gone around the Sun if it had been there 30 Earth years? How many times would a space probe on Venus' surface have gone around the Sun if it had been there 30 Earth? I know what it's saying. What if you landed something on Venus? In 30 Earth years, if you remember how many times did it go around the Sun? Venus orbital period 0.62, so 0.62 of 30, that would be in the neighborhood of about 18. No, I'm sorry, I did the wrong way. Divide by 0.62, and you would get around 48 trips around the Sun. Okay. How many times has Jupiter rotated on its axis in the last 24 hours? Okay, that would be even tougher to figure. It rotated once every 243 days, and then divide that by 24 again. It's going to be a pretty small time, only about 2.66 times in the last 24 hours. That even sounds high. I don't believe that's right, but we'll see. Okay, there's Venus. Mars. Okay, how far is it from us? From the Sun, 1.5 astronomical units. Since we're 1, it's half an astronomical unit from us. So the distance from the Sun to us, half of that is how much it is from us to Mars. So Venus is much closer. That's about 0.28 from us, or 0.3 from us, whereas Mars is 0.5 from us, astronomical units. Geologically active regions, there are inactive volcanoes, no active ones that we know of right now, but you can tell they've been there. There are canyons, and I think in math class, we saw pictures of the canyons. Terrace plateaus near the poles, in other words, pretty flat near the poles. Flat regions pitted with craters for much of the rest. Now, why do you think it's pitted with craters? Thin atmosphere. These two go together. And mostly CO2 atmosphere, whereas Venus is a very thick, dense atmosphere, mostly CO2, but it also has things like sulfuric acid and other things in it too. Not a nice place. Mars, not a nice place because it doesn't have enough atmosphere at all. Okay, there is strong evidence for water in the past. In fact, we have discovered some water just below the surface, especially around the pole areas, in ice form. The evidence that it did have it, the canyons. Most canyons are made by flowing water. We can't think of anything else that could have made those canyons. So there is strong evidence for water and liquid water in the past. Does that mean there's strong evidence of life in the past? No. We haven't detected, as far as I know, because they've sent up some new probes recently. I don't know all the data from them, but I still don't think they've discovered any life. If they have, it's microbes. It's nothing. There's no Martian men that come to Earth. I don't know if you remember, you wouldn't remember because you weren't alive then, but if you've heard the stories, H.G. Wells was a writer, and he produced one, either Halloween, I think it was, a radio show. And he did it so well, and he had such a magnificent voice I think he was the narrator to it, and it was the Martian invasion. It was fiction, but he did it on the radio, and people didn't understand it was fiction. People panicked. They were convinced these green men from Mars were attacking the planet. They weren't. Can you get it to do anything? Is it responding to anything you're doing? No. I'll try and try. It also has numerous space probes. In fact, we have several landers right now on Mars crawling around. You know, can't think what they call them, but they are actual mobile devices that are taking samples, driving around. Rovers. Red rovers. No. Okay. All right. That is what the surface looks like. Okay. There's certain features here that are very interesting. Notice the sort of horizontal structure of these rocks. Later we're going to learn sedimentary rocks come out of solution. So this is other evidence that you must have had water in the past. It looks like you have sedimentary rocks there. Now don't get really fired up. This is where one of our samplers went and took, but this is what the surface looks like. Largely iron oxides on the surface. Okay. Now in your text, you'll see the list of the numerous space probes. And if you look at that one, a bit more US, a bit less lighter on the Russia side. And by the way, the one for Venus, I forgot to note to you, the one on the slide only went to 1989. Two since then, European Space Agency, ESA, and a U.S. one. So Russia's kind of out of the picture. Certainly the Soviet Union is completely gone, but the U.S. and European Space Agency have done more. And you'll notice for the Mars, U.S. outnumbers USSR, but you see a few ESA showing up in there. That's European Space Agency. And then the last one up there, 2014, India sent one up. Interesting. Okay. But anyway, we'll stop there. We'll start with Jupiter next time. Now, there are a couple questions there, but I'm not going to focus too much on the questions. They're kind of interesting to study or to look at, but a lot of them depend on you having had the first half of the book first. And since we haven't, we won't do that. Size comparison of the 4 rocky planets. I think the thing you were talking about probably pretty similar to this one. And you'll notice our moon there is shown to scale almost the size of Mercury. Mars' moon is shown tiny little thing. All right, so we'll start with Jupiter next time. If I think of, oh wait, I'll actually start with some of this stuff. I may actually start with some of these examples. We won't do a lot with them, but we'll do a little bit with them since they're here. Okay. Get the right pages in place. Okay, good deal. Now, do any of you want to take a little time to work on a formula and equation sheet? Okay, well then take that, start working on that now. I will get this thing sort of taken down, and we'll pick up and go. I was afraid I couldn't remember if I had told you you could have one. I think I did early on in the thing, but I don't know if anyone remembered that. Okay. I'll